Hello and welcome back for another VMK in the C++ series. In this VMK, I'll be talking about compression, and I'll be showing you how to use the zlib library to compress data. So first of all, what is compression? Well, if you use the internet, you've been using data compression all the time. What's happening is we have a set of data that we want to transmit over the internet, but the smaller the amount of data that we need to transmit, the faster we can actually transmit it to the other side. In addition, it reduces the cost to the internet service providers to transmit less data from one point to another. So data compression is a good thing. If you've been following along with the other video tutorials on the website, we've already been using data compression here inside of the ogvorbis library. Ogvorbis is a means of compressing audio so that you have smaller file sizes for the actual audio content that you play back to your speakers. We've been using data compression for graphics as well. When we save data in JPEG file formats as opposed to bitmaps, we're actually taking the raw data that represents pixels and compressing it to represent a smaller file size of the same object that was the original bitmap. So there's different kinds of data compression. In this VMK, I'll be showing you how to compress arbitrary data so that you can use it in different projects. Now, if you want to learn more about data compression, I recommend going to wikipedia.org and typing in data compression and have a read through here. You'll learn a lot about the different kinds of data compression, what the differences are between lossy and lossless compression. When you do compression, you can basically take your original source that you're compressing and you can either do it lossless, meaning when you compress it, the data is stored in such a way that when you uncompress it, you'll have the exact same data that you started off with. Whereas lossy compression, this is compression that you would find in MP3s, for instance. You take your original source, your WAV file, you compress it down, but as you compress it, to make it smaller, you're actually throwing away some of that real data. So when you're uncompressing it to play it back, you don't have that pure crisp sound that you used to have. It still sounds good, but it is a lossy compression format. In here, it talks about different kinds of compression. For instance, here's a very simple algorithm for compressing data. If you had a number such as 25.8888 all the way down here, instead of saving all of that, what you could do instead is say, well, let's save 25 point, and then we have all of these 8s in a row, so let's save how many 8s we have, and then what it is that we have. This type of data compression is sometimes referred to as RLE, or run length encoded. So what you're doing is you're counting how many of one type of value you have and then encoding it in some sort of means, so that when you do save this, you have a lot less data to save than the original data that you started off with. And of course, there's different kinds of compression algorithms. You can read about them all down here in the implementation examples. Now in this VMK, I'll be using the zlib library, which is a massively spiffy yet delectably unobtrusive compression library. It's also free and, not to mention, unencumbered by patents, which is great to use in our own projects. At the time of recording, the zlib library is at version 1.2.5. It was released on April 19th, 2010. So when you watch this video, there may be a newer version, which means that there may be some functions that I use in this library that either have changed or may no longer exist. So you may need to read through the help documentation to see what may have changed between the version that you are using and the version that I used in this video. Alright, so to begin, we need to download this guy. Now, what we have down here is a bunch of different versions of the zlib library. We can download the source code here as a targ.gz file, as a bz2 file, as a zip file, or we can just download the DLL. What I'm going to do is download the source code as a zip file. So from the US mirror, I'll just click on that, and let's just wait for that to download. Now that that's done, let's go open it up and take a look at what's inside that zip file. Here's the directory where I downloaded that zip file. If I just uncompress this guy and take a look at what's inside, we see we have the following files. These are all the files that are required to make the zlib library compress and decompress files. And there's a README file in here that you can have a read through to figure out what everything's all about. What we're particularly interested in is the contribution section. And because we're using Visual Studio, we're going to go inside the vStudio directory. And in here we have VC9 and VC10. Now VC9 contains the project files to build the project, and VC10 has the accompanying files for Visual Studio 2010. However, we're not going to be using these because if we go read through the README file, we'll see that what we need is actually available right here from this website, winimage.com/zlib.dll. You can't go through the whole process of building the zLib library to give you your DLLs or your static library, but we can also just download them directly from this website because they're conveniently available here. So that's what I'm going to do. It's a lot easier. You don't have to go through the process of building a lot of these extra projects as described inside of this README file. But that's entirely up to you on how you want to handle this. So let's go back to our web browser and let's go over to winimage.com/zlibdll. Now on here we'll see that we have, because this is just binary data, these first two things here are those two sizes that we saved out, but then everything else is the compressed data. So it's no longer readable because it's no longer ASCII text like this. What we want to do now is be able to take this file and uncompress it and retrieve this original set of data. So let's go back into our source code and give this a try. Okay, so here we are back inside of our source code, and down here, instead of doing all of this stuff, which is all the compression stuff, let's comment all of this out and write the following code. Actually, before we start writing that, let's go back inside of zLib and take a look at the uncompress function. So we saw there's compress, compress2. Down below we have uncompress. So uncompress, what it does is it takes four parameters: a destination, destination length, a source, and source length. So obviously here we need to know the destination length and source length. Those are the two values that we initially stored. We have a source, which is that compressed data that we're going to be loading from our file. So all three of these things we have, and then destination is actually the result of the uncompressed function call. And then if this guy succeeds or fails, it's going to give us an integer back, which we can figure out whether it has enough memory, whether the buffer sizes are the correct size, or whether the data was actually encoded correctly. So all of that stuff will get returned here through that integer. So let's give this a try. First thing we do is we open up a file stream here. Once again, this time we're going to be reading a binary stream of data from our test file.bin. If we are not able to open up this file, then we're going to just display an error message saying cannot open binary file and return out of our function. If we are able to open up this file, then, well, let's start retrieving our data. First thing you'll remember that we stored was the actual size of our string. This is the uncompressed size. The second thing we stored was the compressed size, and the third thing we stored was the compressed data. So the first thing that we retrieve has to be the uncompressed size. So that's ul data size. We're going to be reading it from the binary file and storing it inside of that variable. And after we do that, we can display it to the screen showing uncompressed size and the actual size that we read in. Once we know the uncompressed size, we can create an array of unsigned characters of that size, which will contain the uncompressed data after we uncompress it. Second number that we stored inside of our binary file was the compressed size. So we're creating here a variable for our compressed size, retrieving it from our file, and then we're going to display it here to the screen saying compressed size is, this is the value that we read in. Third thing we stored was the actual compressed data. So it's going to be of this size, so we need to create a pointer to some unsigned character array, and we're going to read all of that data in based on the size that we read in earlier. So without knowing that size, we wouldn't know how much data we need to read in from our file. Once we finish reading that in, that's the only three things that we stored in our binary file, so we can close that off. We're done with it. Now we need to go and call the uncompressed function call from the zLib library to uncompress the data that we've read in into our uncompressed data array. The four parameters that we're passing in here is the destination pointer, the destination size, the source pointer, and the source size. All that stuff we already have. And once this guy returns, he's going to give us a value, and obviously after we uncompress the data, we don't need the compressed data sticking around any longer. So we can go and delete that memory, free it up. Based on the return value here, we can display whether we uncompressed successfully or whether we got an error message. So if we go and get a z_open OK value, then we've uncompressed correctly, and we have some data that we can spit out to the screen or to a file. Because we have a large set of characters to display, I'm just going to dump them out into a new text file called results.txt so that we can compare them easier. We're going to use another stream here called txt file. Open it up. If we can't open it up, then we display an error message. Otherwise, we're going to take all that data that we uncompressed, dump it inside of our text file, and then close it off. If we had any error messages, we're going to display those, and then after doing all that work, we're just going to delete the data set for the array that we allocated up above. So that's it. Let's give this a try. That seemed to build okay. Let's press Control F5 and take a look at what happened here. Well, our uncompressed size is 710,070. That's the correct uncompressed size. The compressed size is 53,109. That's the same number we saw earlier. And it seemed to uncompress successfully as well. So everything looks okay. Let's open up our file. This is the original test file.txt. This is what we're expecting to see from the result.txt file. So let's open up the result.txt file and compare it with this guy. Here's the result.txt. If we open it up, we see, wow, take a look at this. We have all the data, and it all seems to look correct. Let's scroll down here. We see 4883 displays 4883. Everything looks great. However, there is a problem. Scroll down to the very bottom and take a look at the very last line. What do you see here? Well, the line looks okay, but then we have these garbage characters. What's going on? Well, you have to be aware of the data that you're uncompressing. I specifically chose to use character strings because character strings are very deceiving. When you're looking at a character string inside of memory, you may not realize that those strings are actually null terminated. So you have to make sure you account for that when you go and work with them. Well, if you're working with integers, floating point numbers, or data structures, you probably won't run into this as much because your data size will always encompass the data that it contains. However, with strings, you do have this extra thing to worry about. So how do we fix this? Well, it's actually relatively easy if you realize what the problem is. So what I'm telling you here is that we uncompressed the data, but we didn't null terminate it. Originally, in our std string, our data was stored inside of that std string, and it was automatically getting null terminated for us. So we really didn't have to worry about it. However, when we're uncompressing it, we're storing it here inside of this unsigned character array, so that we need to make sure we do account for a null terminator. So instead of allocating an array here of size ul data size, that's only the actual data that we store. We need to add one for a null terminator. Then down here, if we do uncompress successfully, the very last thing we need to allocate here is a null terminator at the end of our data set. So we can take this guy, and we know how large the data set is. It's this size here. And to null terminate it, just set that last value equal to 0. So now, when we run through our code and take a look at the results, notice that the very last set here no longer has that garbage data because we did null terminate it and there was no extra garbage after this last character inside of our array that displayed into our file. Okay, so I hope this was helpful. I basically showed you how to compress and uncompress data using the zLib library. Now, let your imagination run wild. You can use this inside of your games. If you're creating a game and you want to store your data in some sort of compressed format so that you can encode it and pass it on to people, it's a great way to do it. You use the zLib library to take your data sets, for instance, if you have structures that represent monsters in your games, structures that represents players, whatever it is. Take all that data, compress it down into a size, save it into a file, and then you can load it up very easily and uncompress it. Instead of having to store raw data that can be easily ripped out and taken into other contexts, by compressing your data, you're actually protecting it from theft by other people. Unless they know exactly what's being stored inside of that data, they may not be able to retrieve the data that's stored inside of there because they need to know the structure. If I didn't tell you what those first two numbers were or where they were stored inside of the file, you would have a hard time uncompressing the data. So just a few things to think about when compressing and uncompressing data. If you have any questions about this VMK, head on down to www.maticknows.com and go on down to the forums under VMK number 17, I believe, in the C++ section, and post your questions there. Pre-built zlib DLL compiled with Microsoft Visual Studio 2010. This file here and this link here right now point to the same file, which is the file that we want. So let's download this guy, and I'm going to download it to the same spot where I downloaded the previous file. So after that's done, let's go back inside of here and take a look at what we have. Alright, so inside of here we have another README file which describes particularly what we have inside of this file, and it does describe here what it is that we need to do. So you can have a read through here, or you can just follow along in the VMK. So in here we have DLL files for 32 and 64-bit operating systems, and we also have static libraries for 32 and 64-bit. I'm going to be using the 32-bit DLL. So inside of here we have the DLL file and we have our library file. Both of those we're going to need in our project. So let's go back to our root here, and well, let's start a new project since we have all the files that we now need. I've opened up Visual Studio 2008. You can use 2010 if you like. I just don't happen to have it installed on my computer, so I'm going to be using 2008. I'm going to select File, New Project, and we're going to be creating a Win32 console project. I'm going to put it inside of our directory, which is located here, and I'm going to call it zlib test. We can uncheck that and select OK. Under Application Settings here, we have Console Application. We're going to be using precompiled headers, and we don't need any of those. So hit Finish, and I'll create a sample project here for us to begin with. Before I like to begin coding, I always like to set up my development environment. So clicking on the zlib test, go to Properties, and under General, under the output directory, I'm going to rename this to _build. And actually, let's change this to all configurations. Calling that build here. Under the debug section, the working directory is going to be the same thing, _build. And the linker, we're going to have an additional library directory called lib. And let's leave that as it is for now. So under here, we can do a quick test, just a printf statement, just to make sure that everything is up and running. Press Ctrl F5 to build and run the project, and we should see hello displayed here in the black window. Alright, so we've just built our sample project, and to make sure that we've set up the development environment, if I go back inside of the work directory here under zlib test, we see that we have our files that were created with our solution, and now we have a build directory, and inside of here we have our zlibtest.exe. If we run that, we should see that black window appear quickly, show hello, and then it immediately disappears. So that's all good. Now let's start copying files over from those zip files that we downloaded so that we can start using the zlib library inside of our project. I'm going to open another window here to our current directory, and this will make things a little easier to copy from one location to another. So we're going to be copying over some DLL files from our DLL32 directory that we downloaded, and we have our DLL right here. This is the DLL that contains all of the code that we'll be using that is part of the zlib library, and we want to copy that over into the build directory where we have our executable that we just built. The other thing that we want to copy over is the zlib windows API.lib, and we can take that, and we're going to be putting it in here under a new directory that we call lib. So that's where that goes. The other thing that we need are the header files that belong to this library, and those ones we can find inside of the source that we downloaded here under zlib-1.2.5. So scrolling down to the very bottom, we have the zlib.h and zconf.h. Take both of these and we can put them right here into our directory where we have all of the other files. So that should be it. Let's go back inside of Visual Studio now and attach these files into our code. Inside of the zlib test header files, we want to add existing item, and we want to add those two files we just copied over. And now that we have them in our project, let's go and include them inside of our source. Okay. The other thing we need to do is link in to that new library file that we just added into our lib directory. So going back inside of here, we copied over this guy. So I'm just going to copy that file name, and inside of our project settings, under linker, input, under additional dependencies, we just want to paste in that library. Alright, and if we rebuild, we should get succeeded because we really haven't changed any of our code. So now we're ready to start writing some code so that we can start compressing some data. I'm going to be using strings inside of this example, so we might as well go and include inside of stdafx.h our include for strings. I'm going to create an std string called str, and it's going to contain some arbitrary text such as please compress me. So that's the string of text that we want to compress and see how well this compression library works. Because I'm going to be compressing a number of things, I'm going to write all of our compression code inside of a function so I can just call that function multiple times. I'm going to call this function, let's see, compress test maybe. And we're going to be passing in an std string into this guy called str. So from here we're going to call that compress test function, and we're going to be passing in string into it. Okay, so how do we compress data using this Z library? Well, if we take a look at the zlib.h, we can see that there's actually a really good explanation here on how the compression library works. And what we're mainly interested in is scrolling down, down, down. There is a function that we'll be using called, it's near the bottom I believe. Okay, utility functions. There's a function called compress, and there's a function called compress2. The main difference between compress and compress2 is compress2 allows you to specify the compression level, whereas compress assumes a default level, which is approximately level 6, I think, if you read through the documentation. So this is the function that we're going to be using to compress the data. And we can see here that this function accepts 4 parameters: a destination pointer, a destination length, a source pointer, and a source length. And the return value here is an integer, which it determines whether the compression actually happened successfully or not. So inside of our compress test function, let's do the following. First thing we're going to do is check to see how big is the string of text that we're actually going to be trying to compress. So we're going to display to the screen here string length and then the actual length that the string variable returns to us. Then let's go back into here. It says that the thing that we need to do is use this compress bound function to pass in the value so that we know how big to expect the destination to be. So doing just that, we use the compress bound function on the string length to give us an approximation for how large the compressed data size will be. We're going to save that inside of this variable here, and we're going to also print it out to the screen by displaying compressed bound and then that value that gets returned to us. Then, once we know how big the compressed size is going to be, we're going to allocate some new memory of that exact size for this pointer here of unsigned characters. And we're going to then call the compress function. Remember, it accepted 4 parameters. The first parameter was a pointer to our data, so that's this guy here that we just created. The second parameter is a pointer to a unsigned long value that will get updated after the compression is complete. So initially, this is an approximation of how big it is, but after the compress function actually runs, it will update the actual value that's stored in here. The third parameter is a pointer to the actual string we want to compress. So that's the string that we have that was passed in here. We just get a C string pointer to that data, and we cast it over to a pointer of a byte. And then the last parameter is the actual length of the string that we were trying to compress. So that's the source length. Now the compress function will return to us a value. So we'll save that inside of iReturn. And then based on the value that it returns, if it's z_ok, we'll display compress ok. If it's mem error, then we'll display an error message saying compress not enough memory. We could also get zbuff error, which is not enough room in the output buffer, so we basically underestimated this compression data size. And alternatively, if we don't get one of these 3, the library may have changed and it's actually now returning some other value, so as a default I just display here some generic error message with the actual return value. After the compression, we have a new data size stored inside of this variable. So let's print that to the screen by showing compressed size and the actual size. And then as something interesting, let's take a look at the compression ratio. So this is the actual compressed size divided by the original size of the data that it was uncompressed. And for a good data compression, obviously this value should be less than 100%. If it's 100%, that means that we didn't gain any compression because the compressed size is equal to the original size. However, if the compressed size is less than the original size, then that means we did get some sort of data compression, so that ratio would be obviously less than 100%. And then after we're done with this function, we need to deallocate the memory that we allocated up here using the new operator. So we call delete on the data compression data set that we initialized. All right, let's save that out and build our solution here. What do we got here? Compress test. Is returning a value. Oh, I'm returning false here. Well, let's change this up to be a Boolean, and then right at the very bottom here we'll return true if everything goes okay. String is an undeclared identifier. Oh, I only had 1 colon there. We should have 2. And now we seem to build correctly, so let's just clean our solution and rebuild one more time. Okay. So now we're getting some problems here with the linker. We're getting problems saying that we have unresolved symbols for _compress. What that's telling me is it's not linking in to our library, which we have back over here. So let's just double check to make sure that was set up correctly. Under linker, we have our library. And our general, we say it's located in the lib directory. So that looks okay. Oh, I remember. I forgot a key ingredient here to build our project. Right at the very top here, and before we have our include for zconf.h and zlib.h, we need to define zlib_win_API. If you read one of the README files from the downloaded zips, you'll find that this is a requirement for us to be using the DLL inside of our projects. So now let's go and clean our solution, rebuild, and we should be good to go. Okay, so now we've succeeded. Let's press Control F5 and take a look at the results. Our string, our initial string, which was, let's scroll down here, please compress me, was 18 characters long, and the compression bound was estimated to be 31 characters long. It did compress successfully since we have compression okay, and the after compression size was 26. So we approximated 31, but after we compressed it, it was 26. So in reality, we didn't actually get any compression. The compression ratio is more than 100%, so it actually got larger than the original data set, which was 18. So what's going on here? Well, the code is running correctly, but what we're trying to compress here is not a very good example of data that you want to compress. There's different kinds of algorithms used for compression, and I don't know the details of how the zLib library works, but you can imagine that all compression libraries look for patterns within data that you're trying to compress. And in this example here, I have a small set of string text, but there isn't very much repeated data that can be compressed. So the algorithm is actually very inefficient in trying to compress this set of data. Let's try it with a different set of data to take a look on how well it can compress that. Let's replace this initial string with something like 1,000 letter A's. So now if we were to run our program, and I'll put a breakpoint here so you can actually see what str is. All it is a string of 1,000 capital letter A's. So there is a lot of repetition in this string, so we would expect to get relatively good compression. Let's run this through and take a look to see what the results are. So our string length is 1,000. Our compression bound was approximated to be 1,013. And it did compress correctly, and now take a look at the compression size. It actually compressed down to 17. So the compression ratio is 1.7. So in other words, we started with this huge string, 1,000 characters long, and after compressing, we only have 17 characters to deal with. Or I should be really saying bytes, not characters. So we are getting huge compression ratio here because the data that we're compressing is very repetitive, so it works well with this kind of compression algorithm. So you can see, depending on the kinds of data that you're trying to compress, you can get very good compression ratios, or you could get very bad compression ratios. Compression ratio is actually more than 100%, which makes it really not worth compressing the data at all. Now let's take this a step further. Instead of compressing very simple data like this, let's actually compress some real data, save it to a file, and take a look at the results and how you would use this kind of compression algorithm. Compressing data is only one half of the story. What you want to do is take the compressed data and actually uncompress it and be able to retrieve the original data set so that you can use it again. There's no point in compressing it if you can't uncompress it and use it. So what I've done is I went ahead and I created a text file with some data in it. Let me open up this text file and show you what it includes. I've included this text file with this VMK so that you can play with it as well if you wanted to. We're going to put this test file into our build directory. It's called testfile.txt. Contained inside of this test file, you'll find that it contains exactly 10,001 lines. So lines starting from 0 all the way down to 10,000. And on each line we have the number, dot, space, and then a word that describes the actual value. So for instance, if we scroll down to 107, we see that it says 107, and then it has a bunch of dashes all the way down here to, I believe I made this 70 characters long. So everything here is exactly each line is exactly 70 characters long, and there's a number, dot, space, and then words. Okay, so you get the general idea of what this file contains. What we're going to do is we're going to take this file, we're going to compress it to compare its size when it's compressed, and then I'm going to show you how to uncompress it so that you can retrieve the data that's actually stored in that compressed data set. Alright, so going back inside of our source code here, first thing we need to do is obviously load that file into memory, because right now it's in a file, but we need it inside of a variable so that we can use it inside of our compression test function here. The following code will take our testfile.txt, open it up inside of the file stream here, and if it does open successfully, then we're going to go down here. Oh, I guess I should put an else statement. And let's replace this with just the following. So we've declared a std string that will hold all of our data from this test file. We're using the file stream to open up testfile.txt, and if it is opened successfully, then we're going to go inside of this else statement If it doesn't open successfully, then we're just going to display an error message saying cannot open file. After the file has been opened, we're going to take that stream and basically dump it all inside of our std string. Then we're going to close off our file, and then we can pass in our std string into our compressed data function. So let's put a breakpoint right here and run this through and make sure that everything has loaded into memory correctly. Before we can use test file here, we need to also include fstream in our project. So rebuild and give this a try. So we've gone through, opened up the file, dumped everything into str, and we can see here when we open this up, we contain 0 dot space 0 space and then a bunch of dashes, and then after line 70 we have a 10, which is a carriage return. Then we have 1 dot space one for 1 space, then dash dash dash, and then past 140 we have another carriage return, and then we have 2 dot and so on. So you can see all the way down to the very bottom here, which contains 10,000. So let's run that through and take a look at the results on how well it can compress the data. So in total we have 710,070 bytes of uncompressed data. The compression bound is approximated at that. We did compress it successfully, and the resulting size is this. So we are getting a compression ratio of about 7.5%, which is really good actually. So we were able to compress it. Now let's go take the compressed data and save it to a file so that we can see how well that compressed data stores on the hard drive, and then let's load up that compressed data to then uncompress it and take a look at the results to make sure we are actually getting the same data that we started off with. That's the ultimate test. Going inside of the compressed test function call, here we're compressing the data, and here we're basically throwing it away and deleting it. So before we throw it away, let's actually save it to a file by writing the following code. What we're going to do is we're going to use the output file stream. I'm going to call it bin file, and I've called the actual file that we're going to be generating testfile.bin. So we're going to be saving a binary file with the data that we just finished compressing here. If this guy cannot open this new file that we want to create, we're just going to display an error message to the screen saying cannot create binary file. We're going to delete the memory that we allocated up above and just return false. If you don't do this, you're going to get a memory leak, so make sure you don't forget to do that. Then if we are able to open up this file for writing, then we can go and start saving the data. Now, what is it that we want to save? We obviously want to save the compressed data, but we also need to save a few other things. To be able to uncompress the data and retrieve what's stored inside, we need to know how much data is actually compressed. So that's this value here. We have the value because we've compressed the data. We know how much that data has been compressed. We need to save that inside of the file. The other thing that we need to know is how large the uncompressed set of data is, so that when we do uncompress it, we have the appropriately sized buffer to contain it all. If we don't know that size, then we could run into a problem because we're just guessing on how large it will be once it gets uncompressed. So we do need to save these two values inside of our binary file so that when we go and uncompress it, we'll be able to uncompress this data correctly. So to start off, I'm getting the actual uncompressed size of our data here, storing it inside of this unsigned long integer called ul size, and we're saving that to our binary file. That's the very first thing that I save. The second thing that I'm saving is the compressed data size, and then the third thing that I'm saving is the entire compressed data set. So that's an entire string of data that got compressed for us. Then we're going to close the binary file off, so that's going to actually write it to our hard drive, and then we can go and delete everything we had in memory so that we're basically done with it. Let's go run this through. Take a look at the output. Everything here looks okay, and let's take a look at the directory structure to make sure that we did actually write this file to our hard drive. So inside of our output directory here, we see we have testfile.txt. That's the original one. You see that it was 704 kilobytes in size, and here's our testfile.bin. That is the compressed data with those two extra variables that we just wrote out. Now obviously if you try to open up the testfile.bin inside of a text editor, all you're going to see is garbage.